Okay, so at this point, everyone should have watched the video on Blackboard that's titled Find the Derivative of a Function, TI 84 Tips and Tricks, Quick and Easy. So we're going to go past me showing you specific calculator instructions to some of the questions. Okay, so starting with number 6. Suppose that the profits from a business can be determined by the function p of x equals 2,350 sine squared of 0.00001 x squared. If the business is producing 20,000 units per week, is the profit increasing or decreasing, and at what rate? So basically that's saying that x is equal to 20,000 units. Our profit would be P of 20,000, but that's not what they're asking us for. They're asking us for P prime of 20,000. They would like to know, is the profit increasing or decreasing? Increasing or decreasing is always determined by slope, and they want to know specifically what rate. So we're going to go to our calculator. I personally prefer to substitute into the y1 function first. It makes using the calculator a little easier. So I'm going to go to my y equals and have 2,350. Now in my calculator, sine squared is sine of the value. That was 4 zeros after the decimal, 1 x squared. And then I square outside of that to square the sine function. So I'm not squaring the inside, I'm squaring outside after the sine function closes. So I have to open and close the sine function, and once the sine function is closed, I then square. Now I'm going to go back to my home screen, so I used y equals to get to the y list. Second, quit to get back to the home screen. I'm going to use my alpha function to get to F2. So you have an F1, 2, 3, 4, 5. There's nothing actually stored under F5 in this version of the software. So F2 is going to give me my list of calculus things. If you forget what they are, it's perfectly fine that if you go to the first one, you'll see fractions, functions, matrices, which you're not going to use this year, and y-bars, which you're very much going to use. So we're going to go to the functions part. We're going to go to the n-deriv, which is number 3. We're going to take the derivative with respect to the input variable. So x is always on the bottom of the slope, and the y is going to go on the top. So I'm going to go back to that alpha list that I had, the alpha functions, and I want the y-bar function, and I'm going to use the y1 function because that's where I stored the function. And I'm going to put in here 20,000 because that's the input that we have for the x value. And then I'm going to press enter. So my derivative, p prime at 20,000 is approximately, now for the AP exam, you are always going to do 3 decimal places of precision, unless the problem tells you to do something otherwise. 3 decimal places of precision. If you would like, you could change your mode to actually only show you 3 decimal places of precision, as long as you remember to carry forward the exact answer in a problem. So I could do this again, and it would have given me just the 3 decimal places. Because this is a positive slope value, that implies that the profit is increasing. So the way we would actually answer this problem then would be to say that we know the rate, but we want to do this question as an input to output. So we're always going to start with what x variables we're using. So at x equal to 20,000 units per week, because that's the correct notation for the input variable, The profit, which is the function p of x, is increasing because we had a positive derivative at a rate of 937.972, and slope is technically the change in y, or in this case p, over the change in the input, which was x. So the profits of the business, we'll assume for now we have dollars per unit. Okay, now, so another example of using your calculator to answer these questions. Notice how crazy this is. You are not going to want to try to do this in a long string. If you did, you would have to have a parentheses around the numerator and a parentheses around the denominator. Or we can go to our y equals and use our fraction function. So alpha f1, you'll see that's fractions. We're going to do a numerator over denominator. And the numerator is 20. The cosine function has 2x cubed plus x squared plus 1. After I close the cosine function, that's closed off now, I can then square the entire cosine function. So that's 20 cosine squared, whoops, over the function 6x squared, whoops, pressed the wrong button, plus 5. So my function reads almost exactly the way it does on my paper, with the exception of this cosine squared notation, which we can't put the cosine square in the middle of the function like that. So it's going to go after the cosine is closed. And now it asks us in the problem to find the change in velocity. So we have the velocity function, the change in velocity with respect to time, which is equal to the acceleration at any time at t equals 2.5. So we want the acceleration at 2.5 seconds, which is the same thing as doing the derivative of velocity with respect to time at time equal to 2.5 seconds. Now your calculator doesn't care if you've put x values in or t values in. So we're going to quit. We're going to take the derivative. Remember, we're going to get our f1, f2 function values. We need the function derivative with respect to x, because our calculator works in terms of x. We already put the velocity into the y1, and now we simply need to tell the calculator where to take the derivative, and we want that at 2.5 seconds. So our acceleration in this case is negative 20.127. They didn't give us units, so it's really position, but for acceleration it's seconds squared, because we did the change in velocity, and velocity is already a slope. So we divide it again by the s, so seconds squared. The next one says the weight in ounces of a fetus at time t is W of t equals 0.1 t squared minus 0.08 t, where t is measured in weeks. For this one, I'm going to show you. Notice the weight is in ounces. That's the y value. The time, measured in weeks, is like your x value. So we're going to find the rate of growth at 35 weeks, which is the change in weight over the change in time at t equal to 35. Now, I am going to do this one without using the y1, just as an example. I'm still going to do my n-deriv with respect to x as my input. So I'm going to use 0.1 x squared minus, minus 0.08x. So the derivative of w with respect to time, or which we're calling x, at t equal to 35. The problem is when you start to do much of a string on here, it gets a little lost and it's a little harder to see what you're doing. It would have been easier to put it in our y1, but it's okay. And we got 6.920. Now remember, this was weight over time, so that was ounces per week. So what this would mean is at t equal to 35 weeks, the weight, or WT, is increasing at a rate of approximately 6.920 ounces per week. It's not growing the same rate all the time, just at that particular time. Okay, for this next one, it wants us to graph the function. So we're going to start with our y equals. I'm going to clear that out. And our population at any time is 3,000 plus 600 sine. Now I can put this in as a fraction so it looks like it does on my paper by using my fraction function. I must use exact values. I am never, ever, ever allowed to round off pi. So you'll see I have my 3,000 plus 600 sine. If I go back up, if I want to see the whole thing, I'd hit second to the right, and I can see the rest of it. So that was the second button to the right, pi over 6x minus 2 pi. Now I want to graph this on an appropriate window. We're doing the deer population in months for 1 year. That means I want my window to be from time 0 to time 12, because 12 months in a year. And after I've set my x, only after I've set my x, I can press zoom and 0. Zoom 0 will ask the graph to fit that x window. It will never do the x's for you. It will only ever do the y value. So you have to set the x value first. So this was my window. I'm cheating a little bit because I can actually just stretch mine over. You can't do that. Sorry. Okay, so that's the population for 1 year, which makes sense that it's sinusoidal. When during the year is the population a maximum? So that's going to be right here. And it also asks when is the population a minimum? That's going to be here. So we're going to use our calculator's trace button and calculate. So we're going to do calculate second trace, the maximum. Now, left bound means I have to be left of the maximum. So remember this was 0 to 12, so that's 1, 2, 3, 4, 5. So somewhere between 1 and 5. So my left bound is going to be 1, enter. My right bound is going to be 5, enter. It's asking me to guess right now, and I really don't want to guess, so I'm just going to press enter again. So it shows me that the maximum occurs at x equals 3. So the population is a maximum at t equal to 3 months. We always want to put our, and the population at time 3 is equal to 3,600 deer. We'll do the same thing for the minimum, second trace to calculate, this time the minimum. And we want our minimums. This is 12, 11, 10, 9, 8. So we think between 8 and 10. So we're going to say 8 for the left bound, 10 for the right bound. I don't want to guess, so I'm just going to press enter. And we did find out that it was at 9. So my minimum was at 9, 2,400 deer. So at t equal to 9, P of 9 is 2,400 deer, and that's the minimum. Okay, growing the fastest and decreasing the fastest. That's really asking us where we have the derivative, the slope to be the biggest and the slope to be the smallest. So what I'm going to do is I'm going to go to my y equals. I'm going to go to this equals sign here, and I'm going to press enter to turn it off. So I'm not going to graph the function again. What I am going to graph is the derivative of that function. So I'm going to go to alpha f2. I'm going to get my n deriv. Oops. With respect to x, I'm taking the derivative of the y1 function. So I'm going to go tell it to take the derivative of the y1 function. But this time, instead of taking the derivative at 1x, I'm going to take it at all x's. So every x. So the derivative with respect to x of the first function, which was p, I turned off p, I'm only turning on the derivative, at all x's. I'm going to zoom 0 again, because this is a different function. I still want the window to be 0 to 12 for the year, but zoom 0 lets me fit the function again. Now your calculator is thinking pretty hard when it's doing a derivative, because it's estimating them. So you'll notice it graphs a lot slower than it did the original function. It takes it a lot longer to think. As long as it's doing this little process in the top right, it's still trying to process. If you ever wanted to make it stop processing, you could hit the on button, not the off, the on. Hitting on would actually make it break. Not break as in broken, but break the computer process. Okay, so now this is actually our p prime function. So here, notice we have a maximum on the derivative. So a positive derivative here, that meant it was really growing fastest at these two ends. Notice I have a negative derivative here. The most negative is the min. That's going to be where it was decreasing the most. So we have p prime is negative here, where p prime is positive, or the slope is positive at the ends. But most positive meant it was a maximum. So I can press trace 0 and figure out there that p prime of 0 is approximately 314.159, which, by the way, is 100 pi. If I trace and press in 12, notice I got the same thing. So p prime 12 was also 100 pi, or 314.159. And remember, these are slopes, so these are in deer per month, because it's the change in y over the change in x. P prime here in the middle was actually at 6, and P prime of 6 is actually negative 314.159, or negative 100 pi, also in deer per month. So that's when the population was decreasing. So at t equal to 0 and 12 months, P of t is increasing, meaning it has a positive slope, fastest because it was the biggest value for P prime, at a rate of approximately 314.159 deer per month. And at t equal to 6 months, P of t is decreasing fastest at a rate of, decreasing takes care of the negative, so we don't write it, 314.159 deer per month. So decreasing at 314, not decreasing negative. Okay, so you're going to go through and try to work through this part on your own and check your answers online.